Hello and welcome to this session on modernizing your applications with AWS purpose-built databases. My name is Siva Raghupati. I lead the Worldwide Database Specialist SA team. I'll be co-presenting this session with Vlad Vlaschanu, who will come and join me during the course of the presentation. Let's get started. So we are you able to hear me? Okay. So let's get started. So we're what does the AWS Solutions Architecture team comprise us of? We're about 200 plus solutions architects around the world. We're database experts. We work with customers on modernizing their applications on AWS. So I'm going to share some of the best practices that we learned working with customers around the world. Before I get started, let's a little bit of a background about myself. I've been with AWS for the past 13 years. When I started with AWS in 2009, for the first 3 years, I helped build a couple of services. Amazon DynamoDB, which is a NoSQL database service, and then later on Amazon RDS, which is a relational database service. I wrote the first version of the API specification for DynamoDB, and also was a development manager for RDS. So after that, I moved on to the solutions architecture team, and I started building the solutions architecture team and also working with customers around the world and helping them migrate, including Amazon.com. So I'm going to share some of my experience with both building AWS services as well as helping customers on their modernization journey. So in terms of the agenda, we're going to go through some of the key attributes of a modern database applications, and then we'll dive into the database architecture that supports modern database applications, and then I'll also dive into Amazon's modernization journey. So for the past 13 years, I've lived the Amazon modernization journey as it happened. I'm going to share some of the best practices that happened as Amazon, the retail company, modernized their infrastructure leveraging AWS. Then I'm going to discuss, the never-ending mission of a pursuit for an ideal database and how it turned out to be purpose-built databases. And customers often ask us, hey, is there a playbook for migration? So I'm going to walk through, the three playbooks or blueprints that are kind of milestones along the way in your modernization journey. And then I'm going to hand this off to Vlad, who is going to dive deep into a classic modernization journey, diving deeper into purpose-built databases, how you can leverage them as you modernize your application. So we have a packed agenda. So we're going to use the complete, 55 or 60 minutes. And after the presentation, I'll step out and wait for your questions. If you have any questions, please come talk to us. We'll also share our emails. So if you have any questions, you can email us as well. So let's get started. So what are the key attributes of a modern database application? A modern database application should be designed for innovation and agility. It should perform without any limits on performance and scalability. And it should be highly available, easily managed, and cost-effective. Now let's dive deeper into each one of these areas. What does building an application for innovation and agility means? It means the architecture should allow you to innovate really fast. In a recent letter to shareholders, the Amazon, our CEO and president, Andy Jassy, compared iterative innovation to compound interest. So the iterative innovation really creates immense value for customers, and over time, it really snowballs and really exponentially increases your velocity of innovation, if you will. So in other words, your application stack should be able to support iterative innovation. So performance and scalability are quite important. What does this really mean? If you're building a stock trading application, or if you're building an ad tech system that's serving ads, these applications are very latency sensitive. In other words, any loss in latency will result in loss of revenue, and therefore your application needs to meet the performance characteristics of the system that you're building. And scalability, how scalable your application should be. As an architect, if you're building for 6x to 10x is the typical limit of scalability. When you're building an application that needs to meet a certain performance criteria of X, I would advise you to think about 5x to 10x scalability. If your application has to scale to 50x or 100x, now you may completely have to redesign that application, but you can worry about that as you evolve that application later. During the pandemic, scaling up happened for a few customers. I worked with some customers that had to scale 6x in a matter of, let's say, 3 to 6 weeks. This was the scale up that they had planned for the next 3 years that had to happen in 3 weeks to support the kind of workloads that they received. On the other end of the spectrum, the airline industry and the hotel industry saw a massive downturn. They had to scale down as well. So in addition to scaling up, your application has to scale down as well to support the needs of your business. And high availability is critical, which means your application needs to meet the RTO and RPO, recovery time objective and recovery point objective. In addition to that, a lot of financial applications have to have cross-regional DR, data disaster recovery scenarios. And our CTO, Werner Vogels, always reminds us that in large-scale distributed system, things fail all the time. Everything fails all the time. So in other words, when you build your application, you should be building them thinking about blast radius. In other words, your application should be able to gracefully handle failures, if you will. In some cases, your choice of your database will allow you to actually automatically deal with it. For example, if you're using DynamoDB, the partition size in DynamoDB is 10 gigabytes. We actually keep 3 partitions and 3 AZs. Even if 2 goes down, if you're doing writes, we may ask you to retry, but the rest of the application just works. So thinking about availability and blast radius is pretty important. And obviously easily managed, automate everything. Your application should be, you should be able to automate everything and avoid manual processes. Last but not the least, building applications, you need to be cost conscious. Often when you're building applications at AWS, halfway through my design review with customers, I pass and compute the cost and ask the customer, hey, this is the cost profile of my design. Is this, does it actually meet your needs? We often come out with a couple of answers. Yes, let's do thumbs up, let's move forward. Or in some cases, we may find out that the cost, is really high. Having a builder at AWS building services, when we build these services, we build them to do their intended function really well. When the cost is off, chances are you're not using the right service. So this always has been a guiding principle for me as I do design reviews, to be cost conscious and evaluate my design decisions on what exactly the monthly bill is going to be. So with that, let's just, what type of a modern data architecture will support these 7 criteria that we laid about? On the left side, you have a traditional, I would call it sort of a monolithic architecture, if you will, where your web servers, application servers, and database servers. Application tier is a big monolithic application that's actually talking to a database. In most cases, this is a relational database. Even though these various layers allows you to scale themselves independently, really scaling this application is difficult. More importantly, really innovating this application fast is going to be very difficult because there's tight coupling between the various application tiers. And in addition to application being tightly coupled, if you need to make changes in your application tier, you need to be able to talk to other teams. And most of these applications use a single database, if you will. And if you're doing that, then if you're making some changes to the schema, or if your operating characteristic increases, you're going to inadvertently affect your neighboring team or neighboring functionality, if you will. Instead of building, so what is the answer? The answer is actually, breaking the big monolithic applications into microservices and really using a decoupled architecture. On the right side, even though we have 3 layers, if you look deeply there, the presentation layer comprises of multiple pieces. You may want to actually expose a mobile experience to mobile applications, so that presentation layer is separated from actually potentially, serving a desktop application really well. These days, a lot of applications, the users of these applications are other applications. So what you're really presenting is really an application API, an API interface. And then, building that API interface is very different than building a classic mobile applications, which is very interactive. So, kind of thinking of this as, personas that your application is serving, and actually building them as separate microservices allows you to expose the, present the right interface to the downstream applications. As we move down into the business logic layer, instead of having one big monolithic application, you should think of that layer as multiple small microservices that do their intended function really well. And that allows you to implement those using different construct. In this case, you could potentially implement a microservice using AWS Lambda, which is our serverless compute service, or you could containerize that application and use our Kubernetes service, either ECS, container service, or Elastic Kubernetes service, EKS, or you could use Fargate, which is really a serverless service for hosting microservices applications. Now, the difference, as you separate these applications into small microservices, these microservices need to talk to each other as well. In other words, by sending events. And what happens there is you need event queues and message queues. Typically these are, for example, if you're using a Redis stream as a broker, potentially you could, for example, one application can actually send a stream message, and downstream applications can consume that. Other classic scenarios are using, for example, Apache Kafka or Amazon Kinesis as really a message broker. If you are using sort of one-to-one messaging, you could potentially use SQS and other queuing services as well. So the notion of queues kind of comes into play. There's also another construct which is pretty important when you're building this kind of applications, which is really having a mesh. For example, AWS has a service mesh, app mesh that allows you to really have a mesh interface that you can actually send the messages through a proxy layer, if you will. And therefore, you can actually, if you want to actually find out what messages are flowing through which other microservices, you can actually, this is automatically instrumented for you. So even though this looks a little bit complex, you have various other services that you can leverage to build this. And more importantly, each one of the microservice can use its own database. For example, if your microservice is about building a shopping cart, then rather than using a relational database and sharing that with another downstream order management system, you could use actually a non-relational database that can linearly scale with your workload. During Prime Day, for example, we use DynamoDB for that at Amazon. We receive about 80 million plus requests per second, going into DynamoDB. It is very difficult to use a relational database to achieve such a scale. So these decoupled microservice-based architectures enable you to, handle any scale and really follow the cost, if you will. So with that as a backdrop, I'm going to walk you through a little bit of a modernization journey. So as I mentioned before, having been here for 13 years, I was part of this journey when I transitioned from the service teams and became a principal solutions architect. Amazon was my customer. We had this program called Move to AWS, or MOS, it used to call this one, where, I started this journey in 2010 or so, where there's this modernization journey at Amazon really started in the year 2000. Apparently in the year 2000, the entire website was one big monolithic application that was talking to a relational, database backend. So, various teams, shared the different pieces of that application, the big monolithic application. There was also a centralized DBA team that was maintaining these databases. So let's say if an order processing, subsystem had to change the schema, they had to actually talk to the central database, admin team to be able to actually, submit the change and wait for approval. And then each of these various subteams were intricately connected with other teams. Then it was very difficult to actually, innovate really fast and get to market the new products and innovations such as Prime, et cetera, that we invented. So, imagine this was, 1999, the dot-com boom happened, and immediately in 2000, the dot-com burst happened. And then apparently Amazon stock went like 80% down. Even though our fundamentals were very strong, we had to really, tighten up our cost structure, really innovate really fast, right? So with that happening, we had an idea, like what happens if we build this big monolithic, break this monolithic application into smaller pieces and actually break this big, application tier team into smaller sub-teams, perhaps, the order processing team can be its own sub-team, as well as the other team can be. So basically we broke this thing into smaller sub-teams. The shopping cart team could be its own sub-team. And then we evolved this concept called two pizza teams. Now you may be wondering why there's two pizza teams. What it really means is that what is the size of your team? The size of your team should be small enough that 2 pizzas should be able to feed that team was the fundamental idea. Now, well, is it 12 people, 24 people? Well, it really depends upon the size of the pizzas that you order, but you get the idea, that, it should be a fairly small size team. Novel concept, isn't it? Like, this is way before all these microservices came into play. What we're trying to do at that point was, find ways of really innovating fast. That was really the business driver, if you will. So now we found out these 2 pizza teams were really fast and agile. And then they moved really fast as they had complete ownership of the stack. So instead of talking to a central DBA team, if they used databases, they had their own DBA teams, if you will. In some cases, they didn't need a DBA because they used a fully managed non-relational database service. If they need a user experience, if they are presenting a user experience, then the team actually comprised of a UX designer, so they could the whole team could build it. And then sort of the DevOps culture was born from there. So we had this notion that, you build it and you run it. When I was in the early RDS team, we were a team of about 24 people. I was in charge of the backend services. How this really played out in reality was, like, every day at 10 o'clock, we had a stand-up. We all used to go there. We used a Kanban board with the sticky notes all over, and then we just said, look, these are the things that we could do, and these are the blockers, etc. Right? So it became a very nimble culture, if you will, of innovation, and obviously it drove a lot of innovation doing that. But doing that, still, you had to collaborate with other teams, which means we had to put some governance in place. And the first governing structure is having clean API interfaces. For example, the shopping cart system had a clean API that said, add stuff into the shopping cart or list the contents of the shopping cart. As long as that interfaces were well agreed upon, what the shopping cart service uses underneath the covers, what database it uses under the covers is really other teams don't have to care for that. As long as they can maintain their API interfaces. One of the things that we learned was if you build an API, you're going to live with this for a long time. So please think deeply. This is where, the one-way door, two-way door decision comes in, right? Some decisions you can change over time. Other decisions, you're stuck with it for the rest of your life. When we take one-way door decisions, we kind of, halt. We call a bunch of engineers, really review the design. We call our downstream users and ask them a lot of questions, and we make sure that we actually, do something that we can actually stand behind for a long time. So, clean interfaces, establishing clean interfaces was really important. So if you really think about it, this entire transformation was both a people transformation or a business transformation, as well as a technology transformation at the very top. What drove this transformation was actually our business need of really moving really fast. Once we set that as a driving criteria, then we had to put some governance into place, right? Because we're dealing with a lot of customer confidential data. When you log on to Amazon.com and give your credentials, if we lose that credential or somebody hacks that and actually deciphers your password, that is something that we immediately lose trust with customers. That is not something we can afford. So our security teams have put in frameworks. If you're dealing with personally identifiable data, there's clean data classification, for types of data that your services would have to deal with. If you're dealing with personally identifiable data, there's certain criteria you have to go through. In fact, when the retail team uses some of our AWS services, I often used to sit with their security teams, and the security team would ask me all the questions about, does this database, encrypt the thing at rest? How do you transfer, within the database application? Is there any transfer happening where you don't have an unencrypted channel? So those are the governance rules that are put into place. One of the topmost governances, we call this leadership principles. You can look up Amazon leadership principles. When all these independent teams are evolving fast, really operating as an independent company in its own right, or independent business in its own right, you need some strong governing rules. Once you put that into place, then you really liberate the team. The teams can make decoupled technology decisions. They can pick whatever database that they want that really caters to their application need. And then they can also share those interfaces and data contracts and interfaces, if you will. And sort of one feeds into the other. It really created a virtuous cycle, and really, the snowballing effect happened, right? And so I think, even though we're talking about modernizing applications, it's both a business transformation, if you will, and a people transformation or technology transformation, and your company values, starting from when company values and the governance pieces really, play into that journey as well. So now this is a favorite topic of mine. So I've been in the database industry for a long time. Before joining Amazon, I spent 16 years at Microsoft helping build SQL Server and working with customers and partners over there and adapting SQL Server. I've been personally on the lookout for the ideal database. Like, what is the ideal database in the world? So if you're building it, let's say you built a you subscribe to this idea of building microservices, and then the next question customers ask when I do a design review is, what database should I use for my microservice? Well, and they always look for the ideal database. The ideal database now should do everything well, in short, right? It should support all data storage types and access patterns, and it should implement, ACID transaction. ACID stands for atomicity, consistency, isolation, and durability. It should be strongly consistent, and it should scale without any limits. It should be highly performant, and it should be continuously available. Yet it should be simple to use, and cost effective. Now, has any one of you found this ideal database? Please raise your hand. One person has found the ideal database, and the person happens to be on the right end. I'd like to speak with you at the end, because my experience has been this doesn't really exist in real life, right? Well, that might be a sad message. If someone says that this exists, I would like to really question them and have a conversation with them. But instead, what happened over the course of the last 30 years is that we have an explosion of database solutions, right? Starting with Oracle, SQL Server, onto MongoDB, Cassandra, HBase. The open source ecosystem has really evolved tremendously, starting from MySQL, Postgres, MemoryDB, and most recently new SQL databases such as TIDB, Cockroach, and Redis happens to be still the most loved database as per the various reviews, if you will, Stack Overflow, etc. Right? Obviously, we have Memcached, Neo4j for Graph. On the right side, you have all the Amazon innovations, starting with DynamoDB, RDS, Aurora, and to DocumentDB with MongoDB compatibility, Keyspaces with Cassandra compatibility, and so on. So if you deeply look into these things, there's really, if you're a customer trying to make what database to choose decision, it really sounds like a daunting thing, right? And which one do I pick here, right? Actually, if you deeply look into this, the ideal database has evolved into a class of like 7 or 8 different classes of databases. Obviously starting with the relational databases, they've been around for 30 plus years. You model in terms of, rows and columns. There's the various normal forms starting from first, second, third normal form. Everybody knows these things very well. And, it supports ACID transactions. They're really a nice, I think of this as a big Swiss Army knife, right? Has all kinds of tools, but these things don't scale to the level of what we need these times for many of these platforms needs. For example, I talked about DynamoDB supporting 80 million requests per second or more during Amazon Prime Day or during our Black Friday or Cyber Monday. You can get that scale using a relational database. Now, key value databases are very good at that. DynamoDB is a great example. And document databases, developers love JSON data type. This is a great database to actually, if you model something in JSON, to put this in a document data store. Wide column stores such as Cassandra or Amazon Keyspaces, even HBase are pretty good at doing dealing with data sets that have a large large row size, if you will. And graph databases are phenomenal in doing customer 360 kind of use cases, right? And most recently, new emerging time series databases. If you're dealing with time series data, what happens in time series data is what is really what happened in the last 5 minutes or 5 days is a lot more important than what happened 5 days ago or 10 days ago, because you'll never probably look at that, right? If you're sticking all of that into a relational database, the database is going to have a lot of stale data, and this is going to slow down your entire database as you put more and more data into it. Using a time series database automatically deals with that problem. Vlad will get into the details of a time series database as he goes through his portion of the talk. And we recently have ledger databases, Bitcoins and all the other technology has been really popular. People want a cryptographically verified log as to of things that happen here. So ledger databases are also starting to get more prevalent these days. So what this boils down to is the pursuit of the ideal database, turns out to be kind of use the right tool for the job or use the right purpose-built database for your need. So now, with all said and done, really modernization using purpose-built databases. Again, customers really ask me, hey, so all this is good, so where do I really get started? Well, as a solutions architects, hundreds of solutions architects working with thousands of customers around the world, we kind of made, simplified this, into three sort of milestones or three categories that you want to think about, right? Depending upon wherever you are on this journey of your database modernization, right? The first thing we'd like you to think about is really moving to a managed database. We call this playbooks, right? So if you have a self-managed database that you're managing, really moving to a managed database, allows you to delegate all the muck of managing databases, backing up databases, et cetera, to us, so you can use your precious time on innovation. And if you're using, any commercial databases where you are actually, a good chunk of the commercial database use, the TCO comes from licensing costs. If that's the case, moving to an open source database such as Amazon Aurora or RDS will save you a lot of money. And last but not the least, modernizing your applications. This is taking breaking your monolithic applications into microservices and using the right purpose-built database really is on the other, end of the spectrum, if you will. So why is this important? Both modernization and migration is important. Maybe this font might be too small, so I'll read the x-axis here. On the left, you have on-premise systems, moving to sort of lift and shift to the cloud, and then moving to a managed database. The next step being moving to managed database and breaking free from legacy to open source databases, and finally modernizing with purpose-built database. So if you simply lift and shift your workload to AWS, so you may not realize the whole power of the cloud, if you will. Obviously, you have the ability to quickly realize the elasticity of the cloud. But actually, if you use a managed database, you can, as I mentioned before, delegate all the muck of managing the database to us. So what really happens is, if you look at the innovation velocity, it exponentially increases towards the end as you build your monolithic applications into microservices and use the right purpose build. That gives you the most innovation velocity, and your total cost of ownership also decreases as you move from the left to right. With that, I'm going to pass it on to Vlad and have him walk through the modernization journey and get deeper into the services. Thank you.
Hi, everyone. Thank you, Siva, so much. My name is Vlad Vlaschano. I'm a principal database solutions architect here at AWS. I've been with AWS for about 8 years and helping customers migrate workloads to AWS, as well as kind of try to help them deploy business-critical database applications, on AWS using our managed services. So let's dive deeper into this modernization journey. You'll see that it actually looks pretty familiar. So what happened here? So a typical database modernization journey starts here. And it starts normally with a relational database. Not always, but most of the time. The idea here is that you mostly have monolithic applications supporting business-critical use cases where all of the data access patterns were all crammed into this relational model, right? Multiple components, business functions, and so on. So that's one part of that story. The other part of the story is agile startups and teams that are bringing products to market fast. They might be rapidly prototyping on their laptops, on their, on a common code base. They might be using frameworks like ORMs and other sort of tools like that enables them to move quickly and bring a product to market quickly with as little code as possible. And when they often use these tools, typically also land in a situation when they're using relational database, because those are the most prevalent skills, and these ORM frameworks support that very well. But there comes a time when they actually need to modernize. And the first step on that modernization journey is move to manage. I know Siva talked a little bit about this, right? The goal here is to take your databases that you're operating on premises or on your own self-managed infrastructure and move them to a managed database service, such as Amazon RDS or Amazon Aurora. The reason to do this is to reduce your operational burden, right? You no longer have to worry about the operational day-to-day activities like backup, patching, configuration, provisioning, all those things. So you gain agility, ease of management, and cost effectiveness most of the time. And in some cases, you actually gain scalability and performance, especially if you're coming from an environment where you're constrained by costs or budgets, or constrained by older hardware. And to help customers with this first step, we offer Amazon RDS, the Relational Database Service. RDS provides a consistent management experience and automation layer around relational databases. And we offer the widest variety of database engines part of this service. You've got 2 commercial database options, Oracle and SQL Server. You got 3 open source database options. You can pick between Postgres, MySQL, and MariaDB. And we also offer our own managed cloud-native database engine, Amazon Aurora. I'll cover this in the next few slides. But the key here is that no matter which engine you pick, you get a consistency of experience and features. Provisioning, configuring databases, setting up and doing day-to-day backup operations, monitoring the health of your databases. All of these are using the same APIs and the same constructs, regardless of which engine you pick. Same thing with security features and high availability capabilities. All of the actual work of setting that up is abstracted away into a couple of very simple choices. They're either parameters in API calls or they're consistent API calls, right? So that makes managing databases, relational databases, really, really easy. And your choice as far as which one to pick really depends more on your business needs, right? What do you want to do? Do you want to stay with commercial database engines? Do you want to move to open source ones? Do you want to move to Aurora? And all of those are business decisions. They're not necessarily done based on technical limitations anymore. Now, I mentioned Amazon Aurora before, and the reason we have Amazon Aurora is because customers asked us for a relational database service with enterprise-grade features, but delivered with the ease of use and cost effectiveness of open source databases. So that's why we built Aurora. Aurora is a cloud-native database that is built upon an innovative, purpose-built, log-structured storage layer. And that storage layer provides a couple of key capabilities. One, it's automatically scalable. You don't have to worry about provisioning storage. You just store data on it, and it scales automatically up and out and in based on that. 2, it's highly durable. So we're storing 6 copies of data across 3 availability zones, and we've designed it so it can sustain the loss of an entire availability zone plus an additional copy of data and still be operational. And then 3, this storage is distributed, so you no longer have to worry about throughput to your storage system. Now, on top of this innovative storage layer, when you provision an Aurora, you provision a cluster. And that cluster contains a shared volume that is enabled by this innovative storage layer. And then you can get to pick whether to use MySQL or PostgreSQL drop-in compatible database engine on top of the storage layer. And if you choose PostgreSQL, you can have additional compatibility with SQL Server using Babelfish for Aurora PostgreSQL. So that allows Aurora Postgres to effectively interpret T-SQL commands, just like in SQL Server. Now, with these capabilities, we'll also offer the ability to scale horizontally for reads. You can have up to 15 read replicas in a cluster, but they are very low latency because they're enabled by this shared storage layer. And you can also have globally distributed workloads. You can create secondary readable clusters in up to 5 secondary regions. Data is replicated behind the scenes across all of these. Now, Aurora is designed for scalability, but over time we have made many improvements to boost the scalability further. Now, if you look at the traditional database, it's very tightly coupled between storage and compute, even if you deploy it on RDS. So with Aurora, the first step was to decouple the storage, and that's why we have this innovative storage layer where you don't have to worry about I/O throughput because the storage layer is distributed across many different nodes. You just start using it, you don't provision storage. It automatically distributes and scales. And then the next step in that evolution was Aurora Serverless, where we made the compute scale up and down based on demand. So if your workload sends more queries to your database, compute can scale up. Less, it scales down, and you really only pay for the compute capacity that you use. So this is Aurora Serverless. And in preview today, we have Serverless version 2, where the scaling of the compute is nearly instantaneous. It takes milliseconds. And with these capabilities, Aurora has become the relational database of choice for critical business workloads. And one customer example is Redis. So they had a significant operational burden managing their own databases and all sorts of other secondary issues coming from that. So they moved to Aurora PostgreSQL. And they did that to optimize their operations and make the productivity of their engineers, improve that along the way, so that those people can focus on bigger and better things. Now, once customers reduce the overhead and the operational burden, we get to step 2 of the modernization journey. And this allows them to improve the performance of applications and scalability of applications using in-memory workloads. Typical use cases here are caching or offloading of frequently changing data, counters and rankings and so on, right, to data stores that are really designed for that, so in memory. And part of this process can actually be very, very easy because a lot of customers use frameworks, ORMs, and so on, right? And those actually have native support for these capabilities. So it typically requires minimal refactoring, and it's an easy way to gain more performance out of applications. Now, in this solution space, we offer Amazon Elasticache, which is the RDS equivalent for in-memory database engines. We provided for Memcached and Redis. And we also offer Amazon MemoryDB, which is another database in this space that actually offers full durability. The choice really that customers make here is based on how much durability do you need for these data sets. With Memcached, it's an in-memory solution. It doesn't have any persistence, right? It's a relatively simple database, so it's highly suitable for caching, key value type lookups. If you need some level of persistence of your data, then you're sort of looking at Redis and or MemoryDB as an option, depending on the level of persistence you need. And of course, Redis also provides a lot more query features in the database compared to Memcached. And PayPay Corporation, which is one of Japan's leading mobile payment applications, they chose Elasticache Redis to implement their QR code payment service in just 3 months. And they picked Elasticache Redis for the features that it offers, but also for the fact that it's compatible with what gets consistently ranked as one of the most popular databases in the world, which is Redis. But the choice they made was to enable workflows and applications and microservices that are in the critical path of all of their API calls to be serviced with sub-millisecond latencies. And that is really the core of the reason why they picked Elasticache. The idea there is that systems such as authentication, where they get invoked at any given point in time with every API call from their front ends, those needed to have this level of performance and scalability. Now, I mentioned MemoryDB before. MemoryDB is a newer option in our offering, which I'd like to spend a few minutes on. It's a Redis-compatible database with full durability. It's actually the database in AWS that gives you the lowest query latency of any of our offering. And MemoryDB does that by essentially separating out the compute execution engine that's Redis compatible from a transactional log that is multi-AZ durable. So when you write something to MemoryDB, you write it to the Redis execution engine node that then waits for the data to be persisted in that transaction log and only then replies back to you saying, yep, we're good. And then from a scalability perspective, all of the replicas in that cluster will read from that transaction log and allow you to scale your reads horizontally for in-memory workloads. And you get the benefits of sub-millisecond reads, in-memory reads, scaled out for your workloads. Now, by this point in the journey, we've sort of done all the things that are easy, right? We've moved to managed. We have offloaded some of those in-memory workloads. So the next thing is to actually tackle that monolith, right? Peeling away workloads and functionality out of it and implementing it as microservices. Now the microservices then dictate what database solution you pick based on their access pattern, but also based on some very prevailing specific purpose, right? That customers have. And those tend to be agility, scalability, and performance. And otherwise, you're not breaking up the monolith for the fun of it. You're doing it because you either need more scalability, more performance, or you need to innovate faster. And the choices that customers pick for databases in this space are typically non-relational databases that are more geared towards more generic use cases. Key value lookups, document, stores, wide column, and so on. So let's look a little bit more in detail at these solutions. The first one, and probably the most popular one, is DynamoDB. DynamoDB will give you consistent performance at any scale. It's a serverless offering. You don't need to configure servers. You don't need to configure database tuning parameters. You don't have to worry about versions, any of that, right? You simply go and tell AWS to create a table in DynamoDB, and it can be as simple as that. But no matter what scale you're operating on, no matter how big your data set goes, it will scale and it will give you consistent performance. And this is really a key why customers pick DynamoDB. You will have enterprise-grade features with DynamoDB. You will have encryption, backups, all role-based access controls, all of that, security controls. But a key use case for DynamoDB is essentially limitless scale. That's why Amazon relies on DynamoDB for Prime Day, and we were able to achieve, like Siva mentioned, 80+ million requests per second with this system. And that's why other customers pick it as well. The other core feature is global tables. If you have this need to have a globally accessible audience or globally distributed workload, where data has to be synchronized across regions but needs to be accessed really, really fast from every one of those regions, that's when you pick DynamoDB with global tables. Think about workloads where, they're core to your business, authentication, like access controls, where, users from many different places in the world access essentially and try to interact with that system. And that system is core to your business and cannot fail. That's where DynamoDB comes in play. And it supports the most large-scale, critical internet-scale workloads out there. Workloads such as the teleconferencing services provided by Zoom. So it's no secret Zoom saw a significant increase in their usage during the COVID pandemic, right? When we all went and started working from home and started interacting over teleconferencing services with our coworkers. Not even that, my family had countless family events spent on Zoom, birthdays, anniversaries, and so on. All of that was enabled behind the scenes by DynamoDB. Zoom chose DynamoDB global tables with on-demand capacity to handle both of that growth during the last few years, as well as any of the spikes in capacity that they encountered along the way. But DynamoDB is not the only option. If you have a need for more flexibility, if you have workloads that you need to leverage a DocumentDB document model that's MongoDB compatible, more complex document models, that's when you use DocumentDB. And DocumentDB is a lot like Aurora in the sense that you have clusters. Those clusters can have multiple read replicas in them, and they're supported by that shared storage environment. But you get a similar operational experience there as with Aurora as well. You got enterprise-grade features, you have security, you have global clusters if you need to distribute your workload across multiple regions. And DocumentDB is really use cases where you need schema flexibility, content management systems, user profiles, product catalogs, or any sort of use cases where you accumulate events that are schema flexible or semi-structured in near real time and then need to do some analytics with aggregation pipelines on them. So those are really the core reasons why you might pick DocumentDB. And the other option in this space is Keyspaces. Keyspaces is an Apache Cassandra compatible database service. It's compatible with CQL 3.11 with API, and it's serverless, just like DynamoDB. You get to pick, you don't need to define any servers, you don't need to worry about versions, you don't need to worry about high availability, all of that is taken care of. And it's designed for wide column use cases. So these are query patterns where you might need, for example, schema validation, even though they're non-relational, or you need to support multiple independent sorts on the same data set. So after this step, as you're starting this journey of breaking up the monolith, really the next part and the final kind of step in this journey revolves around specialized data sets. So what are specialized data sets? So these are typical data sets or access patterns that have special requirements or they have some unique characteristics. Think about graphs or time series data. Now, sometimes you can actually reverse step 3 and step 4. Sometimes it's easier to break out of the monolith the specialized data sets because they're a lot more obvious, right? If the data is organized by time, for example, and so on. But what we do see in practice is that customers tend to adopt a generalized non-relational databases first because it's a way for them to gain confidence, to understand how to operate in a non-relational environment. And then they pivot over to these more specialized databases. So let's look at a couple of options here. So probably the most interesting here is Amazon Neptune. Amazon Neptune is a graph database. So it allows you to query and store and process highly related data. What do we mean by highly related data? Well, these are data sets where not just the data entities matter, but the relationships between them. The way to think about it is you're not just looking at what the data is, but you're also looking at the strength or quality of those relationships between them. And Neptune is a database that supports the open property graph and W3C RDF graph models, and you can query using the Gremlin and the Sparkle query languages. It is similar from an operational experience as Amazon Aurora. You create clusters. Those clusters can have read scaling, read replicas. It has similar enterprise-grade features, backups, high availability, security controls as well. And it's designed for workloads where you need to implement social networking graphs, or you need to build recommendation engines where the finding entities with similar relationships matter, or fraud detection use cases where you're evaluating the strength of those relationships. But really, it's designed for those use cases where it can query billions of relationships in millisecond latency. And one good example of that is Dream11 Fantasy Sports. So they're one of the largest fantasy sports platforms in the world. And they needed to scale from tracking thousands of friends to millions of friends for any given user. So they built a persistent graph, social graph of all of their friends and followers and users in their system. And they stored it and built it on top of Neptune. And they used Elasticache too as a caching layer in front of it to store counters and store sorted lists of common followers. Now, this is a great idea where this caching pattern doesn't just apply to relational databases. You can use it with any of the other technologies that we've discussed. The other two databases I'm going to cover really briefly are Timestream and QLDB in the next slide. So Timestream is a system to process, store, and capture time-ordered data. This is data where the ordering in time matters. So these could be measurements from IoT devices and systems like that, or real-time events. It provides schema flexibility and the ability to capture multiple measurements per record, and it's completely serverless. You don't have to worry about any sort of capacity there. You just start using it. Now, it does provide you with data tiering. So it has a fast memory tier and a slower magnetic tier. The fast memory tier is really optimized for very quick ingest of high volumes of data as well as point queries. And the magnetic tier is optimized for storing data long term as well as analytical queries. So the mix of these two, you can set up tiering policies, and Timestream will automatically tier and move the data between these two tiers for you. So this is great for use cases where you need to do trend analysis or forecasting, right? Anything that's based on time. And the last database I'm going to touch upon is QLDB, or Quantum Ledger Database. So this is a ledger. It provides two key capabilities. It's immutable, meaning any change that you make is append only. And you can track all of the history of all the changes in time. This is what the ledger is. And the second key capability is it's verifiable, meaning all of the changes are cryptographically verified, that at any given point in time, you can verify a specific change is valid, is accurate, it's correct. So if you have workloads where you need that, that's where you would use QLDB. It's also a serverless offering. It's fully managed. You can query it with Amazon Particle, which is similar to SQL, but it's also more adapted towards, kind of semi-structured data models, right? And really, it's designed for systems of record, for example, for financial transactions or audit databases or systems that need to track state. The way to think about this is you don't only need to query the current data or interact with the current data that's stored in QLDB, but you also need to prove that that current data is valid or accurate. So this is really the use case that QLDB will solve. Now, if you've gotten to this point, right, you probably no longer have that central database in the middle. Yeah, you've peeled off all of the all of the workloads and data sets that really don't need to be relational out of that central database. You probably still have relational database, and they probably still support core business functions. But the relational database at this point just supports what you need, the core piece, what they're designed to enable. So what happens next? Well, the next step is to go beyond transactional needs, to adopt a business-wide unification strategy that can enable you to take more value out of your data, to use analytics and machine learning. And to do that, you typically would deploy one or more data lakes as a centralization point where all of these databases feed into or feed out of. But this is probably a topic for a different discussion. There's a couple of sessions here at the summit that dive deeper into this modern data architecture and what happens next, past the transactional workloads. So I recommend you check those out. But to summarize, most modernizing with purpose-built databases is a journey, and one that you're probably already on, might not have realized it yet. But all of these steps are designed to enable some of those key 7 pillars or attributes that Siva was mentioning at the beginning of the presentation. And you have different database solutions at every step of the way that would enable you to be more agile, to get more performance, more scalability, easier management, cost effectiveness, and high availability. Now, I promised you a couple of follow-up suggestions for sessions. I'll leave this slide up for a few seconds so you can take a picture of it. And also, we offer many resources to help you boost your AWS cloud skills. So get in touch with training and certification today and check out some of these resources that they offer. And with that, from both Siva and myself, thank you very much for participating in our session today.